Hi, I want to take a look at the, strictly speaking, time-independent, one-dimensional Schrodinger equation and how it applies to the problem of the infinite square well. Now, the Schrodinger equation for one dimension, if we can say that we have a time-independent system that space and time totally decouple, which they will here, the Schrodinger equation is minus Planck's constant over 2 pi, which is h bar squared, divided by 2 times the mass of our particle times the second derivative of our probability wave function, or eigenfunction, plus the potential energy times our wave function equals the discrete energy solutions that we get, or eigenvalue E times our wave function psi. So for the case of the infinite square well, our potential is 0 as long as we're in a region between x equals 0 and x equals L. So all this does to our wave function is break it down to say that the second derivative of our wave function is equal to minus 2 times the mass of our particle times our discrete energy E divided by h bar squared times our wave function. So that means we need a solution where the second derivative is minus our original function, so we'll choose a wave function psi of x of the form psi of x equals a times the sine of our wave number k times x plus b times the cosine of our wave number k times x. And sine and cosine are both, without any other knowledge, perfectly valid solutions. But with quantum systems, there are normally 4, but here 3 rules that we have to make sure are followed. The first thing is if we sum up our wave over all of its existent region, it has to be normalizable. We have to be able to take the integral of our wave function and set it equal to 1. Now, a sine function and a cosine function extend on infinitely. And you would just keep getting a larger and larger value. But we don't have a continuous wave function. We've stopped it at x equals 0 and at x equals L because we have that infinite potential barrier, which is what removes condition number 4 from our list of what has to be done with our wave equation. So instead of minus infinity to infinity, to normalize, we would just end up going from a lower limit of x equals 0 to an upper limit of x equals L. Now, the next piece that we have to look at are the limits. As x approaches plus or minus infinity, it has to go to 0, and x has to be finite, or psi has to be finite as x goes to 0. Well, again, we can't go all the way to plus or minus infinity. We're stopped at x equals 0 or x equals L. But that means we need a wave function where at x equals 0, psi equals 0. So that means that for our cosine term, b has to equal 0. So we've thrown out that half of our wave function. And we're still left with a sine of kx. So we can keep going. Well, the next piece that we would have to consider would be the limits as x goes to L. Well, at x equals L, the sine of KL would have to equal 0, so KL would have to be equal to n times pi. So that means we get a value for k where k has to equal n pi divided by L. Now, the third condition, our function has to be continuous and single-valued. Sines are continuous and single-valued functions. That's fine. And we don't have to worry about derivatives and making sure derivatives are fine because we have that infinite potential energy on either side of this region. So, if I were to plug in my wave function that I've just determined into the Schrodinger equation, I take 2 derivatives of a sine of kx, and that gives me minus a times this constant k squared times the sine of kx, that would equal minus 2 times the mass of our particle, which is usually an electron, times our energy, our discrete energy level, our eigenvalue E, divided by Planck's constant over 2 pi squared, h bar squared, times a times the sine of kx. Well, the minus a sine kx cancels on each side, and that means that our discrete energy levels would be our angular wave number k squared times h bar squared over 2m. Well, k is n pi over L. H bar is h over 2 pi. Those pi's are going to cancel out. But I still have those 1/2s in the denominator, so I have 1/2 squared over 2. I end up with a total of 1/8 in the denominator, or 8 in the denominator, the total value of 1/8. And my discrete energies would be equal to our quantum level n squared times Planck's constant h squared divided by 8 times the mass of our electron, or whatever particle, but like I said, almost always an electron, times the length of our box squared. Thanks for watching.